Hello ST314. This week we'll be learning about regression, and this video is intended to help you go through Minitab and do a regression analysis on your own for your homework. Okay, so this week we're going to be looking at ST314 example PET modulus. Again, if you're in the Umbrella server, all you need to do is click on this link and it will open up a Minitab worksheet for you. Okay, so this particular problem that we're going to look at is from some researchers that wanted to study the mechanical properties of spun PET LCP blended fibers. They wanted to know if the modulus depended on the percent of PET in the fiber blend. Okay, so we can actually answer this question of interest by doing a regression analysis. Now it's a simple linear regression analysis because there's one explanatory variable and one quantitative response variable. Okay, so how do we look at two quantitative variables? We first need to create a scatter plot. So we can easily do that by going up to Graph, click Scatter Plot. We want to choose the simple, press OK, and we needed to choose which one is the y variable and which is the x variable. Well, y corresponds with the response variable, or the thing that we'd like to be predicted, and the x variable corresponds with the explanatory variable, the thing that we feel like is a good predictor for our response variable. Okay, so from here you can actually create a label for your plot. So under labels you can type in scatter plot. And you can put in whatever you'd like there. You don't need to make it too fancy. Okay? And I would actually put in then the names PET and modulus if I were doing this for my homework. Okay, so what can we see from this scatter plot? Well, we can see that it looks to be a strong negative linear relationship between the percent of PET and the modulus. Okay, well, how can we say that? Well, we can see that it's a strong relationship because all these points seem to follow tightly in a particular relationship. We can definitely see a pattern happening here. Okay, why is it negative? Well, as the percent of PET increases, it looks like the modulus is decreasing. So because the explanatory variable and the response variable are actually going in separate directions, we have a negative relationship. Okay, and finally, why is it linear? Well, it looks as though we could actually draw a straight line through these points. That means that we have a linear relationship. If we saw a quadratic curve or maybe an exponential type curve, then we would say that this was not a linear relationship. Okay, so we can look at a scatter plot to kind of do an initial analysis. It's just like looking at a histogram or stem and leaf plot when we want to look at the distribution of a data set. We want to look at the scatter plot to do an exploratory initial analysis. We can also then quantify this particular relationship by doing the correlation coefficient. We can do that by going to Stat, Basic Statistics, Correlation, and clicking on PET and modulus. Now the correlation coefficient does not distinguish between an explanatory variable and a response variable. It's just between two quantitative variables. Okay, and so here we can see that the correlation coefficient is negative 0.987. So this depicts a very strong negative relationship between the percent of PET in a blended fiber and the modulus. Basically, this is just confirming what then we saw here in the scatter plot. Okay, well, why am I doing a correlation coefficient? The correlation coefficient is nice and simple linear regression because it not only gives the relationship between the two quantitative variables, but it also gives the either negative or positive association. And so in contrast to then the coefficient of determination, the R squared value, it gives us this then direction. Okay, so I like to use this when we're doing simple linear regression. Please note that if you were to square negative 0.987, you would simply be obtaining the R squared value for this particular analysis. Okay, so next, how can we get a regression equation for these two quantitative variables? So we can go up to Stat, Regression, regression. And here we're going to perform the regression analysis. Okay, so let's go ahead and choose our response variable, modulus, our predictor variable, PET, and from here we can choose a couple of different things. Under results, we want to click on this and press the second option. Basically, Minitab just gives us too much information. We want to try to minimize some of the output, so we want this second option, press OK. Next, we want to give our residual plots for this regression analysis at the same time. So let's go ahead and click on graphs. And I like the 4 and 1. Okay, so click on that, press OK, press OK. And here are our residual plots. We'll talk about those in just a moment. Let's move them aside. And over here we can see our output from our regression analysis. It looks like the regression equation line is then modulus equal to 8.22, that's our intercept, minus 0.0602, that's our estimate for our slope coefficient, for then the percentage of PET. Okay, so it's nice because Minitab gives us here the regression equation, simply just outputs it for us. Now we can also see that these values here, the estimates for the coefficients in this table, also then provide the same information that's just given up here. So these are the exact same values. Negative 0.06065 simply is just rounded up here. And here for the intercept estimate for the coefficient, 8.2206, is the same as up here, 8.22, again just rounded. So these are our estimates for our coefficients for the constant or the intercept, that's denoted as beta naught, and PET, denoted by beta 1 in a simple linear regression analysis. Okay, so this table is really nice. It gives us some other information other than just the regression equation, and I'll talk about that in just a moment. All right, so moving on, how do we know if our regression equation is a good fit? And so to check the assumptions, we need to look at our residual plots. Okay, now because there's so few data points in this particular example, some of the residual plots might seem to look like they have a violation of assumptions, but really it's just because we have too few values to even make, to say either it's violated or not. And so we're going to say all the assumptions here are met. Okay, it looks like there could be a possible violation of the constant variance assumption here just because that these values seem to be maybe getting a little bit further away from our reference line of 0, but in reality we're not going to worry about those. Okay, so the normal probability plot is a nice plot to look at whether or not the normality condition is met. And we can see that if all of these points follow along the line, this little blue reference line, then we have normality. Now they look like they're following pretty closely, so looks like the normal condition is met. You could also look down here at the histogram of the residuals. Now again, because we have so few values, it doesn't really seem to make sense to look at this particular histogram too stringently. Just kind of look at it and say, it looks pretty symmetric. Okay, all right, so we're going to say that all the assumptions are met and we're going to move on. All right, so how can we perform a t-test for our slope? We can do that by coming back up here to our regression output, and we notice that here there's our coefficient of estimates, then there's a standard error of our coefficients, and then there's a t-statistic. Basically, this is simply this number divided by our standard error of the coefficient is equal to then our t-statistic, negative 13.82 in this particular example. That would correspond to a p-value of 0.000 or less than 0.001. That's how we want to denote this. Okay, so what are the degrees of freedom associated with this particular t-test? Well, it's n-2 for simple linear regression. Okay, so if we were to look up negative 13.82 in a t-table for n-2 degrees of freedom, in this case that would be 5, then we would find a p-value that was most likely off the table. So we would say less than 0.001. Okay, so what can we say then from this particular analysis on the slope? Well, basically it's just telling us that the null hypothesis should be rejected, that the slope coefficient is equal to 0. There's strong evidence to indicate that this is not true. Okay, so that means that there's strong evidence that the percent PET is a significant predictor of modulus. All right. Well, whenever we do any sort of hypothesis test, we typically also do a confidence interval for the same estimate. So how could we construct and interpret a 95% confidence interval for the slope of percent PET? Okay, well, note, Minitab does not automatically calculate this for us. However, we can use this information here, the coefficient and the standard error of the estimate, to simply construct a confidence interval. As we learned previously, every confidence interval is simply just the estimate plus or minus the critical value times then the standard error of the estimate. Well, we have two of those items. We have our estimate and we have the standard error for our estimate. Okay, now all we need is the t critical value for n minus 2 degrees of freedom. So the t critical value in this case is 2.572 obtained from a t table. Well, how can we describe then this 95% confidence interval? Well, the 95% confidence interval for the slope of percent of PET estimates every 1% increase in PET with a PET LCP blended fiber, the average modulus will decrease by 0.072 to 0.049. So basically we can describe this relationship similarly as we did with just the beta coefficient, but now we need to talk about it in the context of the 95% confidence interval. Okay, the main thing that you say in your confidence interval is that you're talking about the average modulus or the predicted modulus. Okay, so the predicted or average response. Okay, so now how can we predict or construct a 95% confidence interval for a particular value? In this case, I wanted you to look at the prediction for percent PET at 25%. How would we go about doing that? Well, we can go back up to regression, stat, regression, regression, and here let's go ahead and remove the graphs. Now what we want is we want to get a predicted output. So under options, we can actually here put in predicted intervals for new observations. We're going to put in 25, and it'll give us a 95% prediction and confidence interval. Click OK. OK. And here we are. We've been given our estimate for when the percent of PET is 25. So this is the fitted value. This is the standard error of the fitted value. And this here is the confidence interval and the prediction interval. As we've learned in reading or in our notes, that the 95% confidence interval is the interval for the average response for the explanatory variable 25. Now the 95% prediction interval is no longer the average response, but for one particular value. So we could see that if we want to just predict one value, then our error will actually get larger. And so the prediction interval is larger than the 95% confidence interval. All right. So we can easily then talk about these 95% confidence interval and 95% prediction intervals just as we have with the beta coefficients and just how we have with any other estimate that we've talked about. We can describe them with the 95% confidence interval and 95% prediction interval. Okay, this was an analysis of a simple linear regression problem. The next video will show you how to analyze a multiple linear regression problem.